In this video, I'm going to be showing you how to use the Harris Benedict equations in order to estimate the caloric intake need in order to maintain body mass. Of course, if you eat less than this, you are going to lose body mass, and if you eat more than this, you're going to gain body mass. All right, so let's first look at the equations themselves. And there is an equation for men and there another equation for women with these. And so here is the men's equation on top, and here's the woman's equation on bottom. They're fairly similar in the way they're constructed. These are both forms of regression equations. So we have our y-intercepts, we have the constant values multiplied against the kilograms of their body weight or body mass. We have the constant values multiplied against their height in centimeters, and we have the constant values multiplied against their age in years. Okay, so most of these are going to be added together once we get to that point of actually doing the equations here in a second, except for the age, which is a negative factor that lowers the caloric intake need. Keep in mind these equations are just for doing an estimate of basal metabolic rate or resting metabolic rate. These are not total energy need. I will show you by the end of this, though, how to get that into a total energy need by estimating their additional caloric intake based on their activity level, so how much physical activity they do. Another quick note on the Harris Benedict equation before we do this is that these are very old equations. They're still used. These are from 1919 though, so they're over 100 years old. So there is some critique out there these equations are too old, and that the culture over time and their diets and the way that we are active have changed, and so these may not necessarily reflect perfectly today's culture and today's people. They still do a reasonable job, but there are other equations out there that are a little more modern, but again, Harris Benedict equations are still used frequently. I do want to point out that these equations here, these are the equations that I'm showing you are the original equations from that 1919 textbook, or that book that came out. And so these equations have a lot more decimal places in the constants than what you typically see when you see this equation out in a modern day textbook or online or something. It's the same equation, it's just they've rounded the decimals off. Does it affect things? Probably minimally. I just decided to stick with the original equation for this purpose. So let's go ahead and get ourselves to an example problem, though, in order to figure out how to use these equations and solve for energy need. All right, so we have Pete, who is 183 pounds. He's 6 foot 1 inches tall, 36 years old, and he is very active based on a sort of quick interview you do with him in order to figure out how much physical activity he does. So this would be basically somebody who is an athlete or has a very intense job. They are asking you to estimate the calorie need in order for them to maintain their body mass. And of course, in this video, we're using the Harris Benedict equations. All right, so here is that Harris Benedict equation for men that I already showed you. So we'll kind of skip past that for now. But what we do need to know is everything is in metrics, so we do need to convert the weight to kilograms and the height from feet and inches to centimeters. All right, so let's do the weight first. So he's 183 pounds, divide that by 2.2. That gives us 83.18 kilograms. The height of the person, he was 6 feet 1 inches tall, so 6 feet times 12 inches per foot, plus the extra inch gives us 73 inches. Then 73 inches times 2.54 gives us the centimeters, so 185.42 centimeters. Note that I'm going to be keeping all the decimal places as I go, just to make sure I don't have any rounding errors. And I'm going to do this probably to an excessive level. You certainly don't need the level of decimal places that you'll be seeing me do here in a moment. All right, so let's move on from there. We have, again, here's that equation, just copy and paste it again. Here is that same equation filled in with his values. So we put his weight here, so the 83 kilograms. We put his height here, so the 185 centimeters. And we put his age here, the 36 years. The first thing I'm going to do is I'm going to do all the multiplication. So each set of multiplication first. So we end up with this after doing that. So then the next thing I did is I did just the addition, added these things up here. So these three different terms, and we got this one here, the 2,138 with lots of decimals, which again, I'm just keeping all the decimals till the end. And we still need to subtract out the term related to his age. All right, so once we do that, though, we get 1,894.86, so on and so forth, for the kilocalories per day of resting energy expenditure. Again, that basal metabolic rate is what these Harris Benedict equations are estimating. So rounding that off, though, we get 1,895 kcals per day. Just to give some context here, the probably other most commonly used formula, and one that is likely a little more accurate for today's cultures, that is this Mifflin-St. Jeor equation. I've already done this as well. I've made a video showing the Mifflin-St. Jeor equation for this exact same example, and I'll put the link in the description below to that. But just to kind of compare the values here, for Harris Benedict, we got 1,895. For the Mifflin-St. Jeor, we got 1,816 kilocalories per day of resting energy expenditure. This is not total energy expenditure yet. So if you just ate this level, you would be losing weight because it's not accounting for your physical activity. All right, so now let's go ahead and account for the physical activity part of this. So in order to do that, so total energy expenditure is now what we're looking after. We need to multiply the resting energy expenditure that we calculated up here, and we need to multiply that by an activity factor based on their level of activity. All right, so let's look at some activity factors. So for a sedentary person, so somebody who basically just kind of sits and walks in order to get around the house, and that's really it, you have an activity factor of 1.2. Light activity, so this is somebody who maybe has to go out and about and carries some groceries every day, or goes for a really short walk around the block just to kind of get their dog outside to go to the bathroom or something like that. Now we're talking about 1.375 for the activity factor. Next one is moderate activity. So this is going to be somebody who probably, instead of just walking around the block, maybe they're going to, walk at a fairly vigorous pace, not vigorous, but a brisk pace, and, do it for 30 minutes a day or something like that. Now we're talking 1.55 for the physical activity factor. Then we have very active. For example, this would be somebody who maybe does 30 minutes of activity, but instead of it being walking, it's running. Somebody who does some vigorous physical activity, who like maybe they go out and play basketball every day for an hour or something, where there's going to be a fairly high level of caloric burn from the activity. Now we're talking 1.725 for the physical activity factor. And the last one here, exceedingly active, is 1.9 for the activity factor. And this is somebody who their job is very physical. So they're active for 8 hours a day, or maybe somebody who is a really high level athlete, the type of person who's going to be exercising 3, 4, 5 hours a day. That's this kind of person here. And I'm kind of very briefly describing these categories. If you look online, look in various textbooks, most of the physical activity factors you see are going to be these values here. They call the categories slightly different names depending on the source you're looking at, and they will typically have a description of each category that is fairly similar. To be quite honest, I haven't been able to find the original source for this. So if you know the original source for these physical activity factors, please comment below. I would love to find that original paper or where these come from. But they seem to be fairly commonly used both in research, in practical application, and you can see these kind of all over the place when you start looking this stuff up. But I've yet to find an actual citation for this. So again, if you can help me out with that, I'd be very appreciative. So let's again go ahead and do this last step where we figure out the total energy expenditure accounting for activity level. All right, so this person was very active, so the activity factor for that was 1.725. All right, so again, here's that same equation. The total energy equals resting times the activity factor. So the resting energy expenditure times the activity factor. Plugging all that in, I kept all the decimal places from this value right here for the resting energy expenditure. Multiply that by the 1.725. We get 3,268.6 with all these extra decimals kcals per day. Rounding that off, 3,269 kcals per day in order to maintain their body mass while being very active. Of course, again, if they eat less than that, they lose weight. Eat more than that, they gain weight. Comparing once again to the same person doing the Mifflin-St. Jean equations using the same activity factors as this, it's 3,132. So a little bit of a difference here. So we're talking about 130 or so calories. Not a huge difference, but that's a reasonable difference if it's something that's going to be adding up every day. So these both have some error to them. They're both estimates, but they're both probably reasonable. Again, the Mifflin-St. Jean, a lot of people think it's better, but the Harris Benedict's been around forever, basically, and people use it a lot. All right, so let's go ahead and do an example using a woman as our participant. All right, so we'll go through this one a little bit faster since it's basically the same process, just a slightly different equation. But we have Tina here, who's 135 pounds, 5 foot 3 inches tall, 24 years old, and she reports through a sort of interview from you to figure out how much activity she does that she is lightly active. So estimate the total calories needed in order to maintain the body mass using the Harris Benedict equations. All right. So here is the woman's equation. I already showed you that table of those. So it is slightly different. Each constant value is different. So make sure that you are using the correct one and not using the man's equation in place of the woman's, and so on and so forth. Starting off by getting everything into the metrics system here. So 135 pounds, let's start weight, divide that by 2.2, we get 61.36 kilograms of body mass. Her height was 5 foot 3 inches, so 5 feet times 12 inches per foot. Add the extra 3, we get 63 inches. 63 inches times 2.54 as the conversion factor to centimeters gives us 160.02 centimeters tall. On to the calculations. Again, here is that same equation, just copied and pasted. We've already covered that. And here it is plugging in her value for her weight, her height, and her age. Again, we're going to start off by doing all the multiplication first. We end up getting these values here when we do that. Then we'll do all the addition next. We get 1,537.8 yada 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 for that value once we do all the addition. Once you subtract out the age portion of the equation, you get 1,425.6, so on and so forth. For the resting energy expenditure, again, resting, not total energy expenditure, and we'll round that to 1,426 kcals per day. The Mifflin-St. Jean equation for the same example gives us 1,333 kcals per day. So, 80 or so kcal difference between the two equations here again. The rest of this is coming up with the total energy expenditure, which again was resting energy expenditure that we just calculated times the activity factor, and she reported being lightly active. Scrolling over just a second to show those. So the lightly active is 1.375 for the activity factor, and that's what we have right here for the activity factor. So plugging all this together, we have 1,425.6 so on and so on. For the resting energy expenditure, multiply that by the activity factor of 1.375. We get 1,960.2 in a bunch of decimal places kcals per day for total energy expenditure. Rounding that off, we get 1,960 kcals per day of energy expenditure for her to maintain her body mass. This is going to be a little bit different again from the Mifflin-St. Jeor equation, where we got 1,832 kcals per day in place of the 1,960 kcals per day for the Harris Benedict equation. All right, so again, I'm going to go ahead and put a link in the description below this video to the Mifflin-St. Jeor example video, where I use these same two individuals' profiles in order to calculate their caloric intake need. Mifflin-St. Jeor equation is a much newer equation, so culturally we are much more similar to the people that were in that study. Maybe a slightly better equation, but again, people use both of these out there.